Now that you know how to mutate a linked list, let's think about how to do that recursively. And some interesting opportunities arise with the extra power of recursion that aren't available with loops. Let's start by looking at our loop code and reminding ourselves what it does. We'll start here at line 12, attempting to insert 31 into the list shown here. The test on line 12 will return false because first is not null, it's a pointer to a node, and first.item is 11, which is not greater than or equal to 31. So control will move to line 15, where a new variable is going to be declared as an alias to the first node. So this first will be stored in a new variable called x. We then enter our loop while x next is not null and the x next item, that's not the item x is pointing to, but the next one, is smaller than the parameter, will continue to loop. Note here that it's very important that we know that x is not null before executing line 19. We've already checked that first is not null. We've assigned x to first, so we can assume that x is not null at this point. Since the condition of the while loop is satisfied, we'll advance the pointer on line 20 and go back around to check the condition again. Again, x next is not null. It's indeed this node with item 41. But in this case, the item of x next, which is 41, is not less than our parameter. Therefore, we'll exit the loop and go on to line 22. Here we create a new node, and the constructor will return back to us that new node with item 31 and next pointer referring to x next. After the constructor returns, we will then update x next so that x next is no longer referring to the node with 41, but instead referring to the new node. So this object with 31 is going to get pasted in between, and we're done with our loop. Anything we can do with a loop, we can do with a recursive function. And so I can mindlessly apply my algorithm for converting loops into helper functions, and I'll arrive at the following. Here's a direct translation of my while loop as a recursive helper function. Instead of starting the loop, I start the helper function. The loop has two variables that it mentions. These are x and item, and therefore these are the two parameters of my helper. I'll initialize them appropriately. First is the initial value of x, and therefore I will pass in first to the helper to kick it off. In my loop, I was checking the bound repeatedly and advancing x. In my recursive function, I check the bound once and recur, updating x in the recursive call. In the base case here, once I've finished with my loop, I'm going to update x. Likewise here, in the base case, when I'm finished with my loop, I'm going to update x next. You can see that this code has two similar looking blocks. The first block in the starter function handles the case that I might insert at the first position in the list. And the helper function here handles the case that I might insert somewhere else. Let's look at examples of both of these cases. So suppose I want to insert item 11 into the list that begins with 21, 31, 41, 51. In this case, at line 12, the condition will be true. First is not null, but first item is greater than my parameter. And therefore, I will execute line 13, calling the constructor to create a new node. The constructor will return the new node with item 11 and next, pointing to the current value of first. So note we're going through this first. We're going to copy that value into the node's next field. Then I'm going to update the first variable. And so this item is going to be stitched in between the playground object and node, and therefore it becomes the first item on the list. Now let's look at what happens if I'm inserting a node somewhere further down the list. To do this, I'm going to translate the code just slightly to make it look a bit more natural. Here I am checking the loop bound and then recurring. It's more typical in a recursive function to check for the base case, in which case my code looks like this. Note that with this rewrite, the code on line 19 is now almost identical to the code on line 12. The only thing that's different, on line 12, I'm checking first and first item. On line 19, I'm checking x next and x next item. But note that the code is no different from what I had before. All I've done is swap the two cases of the condition. So I'm replacing the and with an or where both of the two are negated. Now let's look at an example where I'm attempting to insert 31 into the list with 11, 21, 41, 51. In this case, line 12 will be false and therefore we'll jump to line 15 and start our helper function. Our helper function is going to be kicked off with x at this first and the item being the same as the parameter that was passed in. On line 19, the condition will be false. Although x next is not null, it is the case that x next item is 21, and 21 is not greater than our parameter 31. Therefore, we'll go to the else branch and execute line 22. This causes a recursive call. In the recursive call, x is bound to our former x next. Call number 3 has x set to the node with item 11. The next call, number 4, will have x bound to x.next from the previous. So we've advanced x. In the recursive call, we'll again check the termination condition. In this case, again, x next is not null. It's the item with 41. But in this case, x next item, 41, is indeed greater than the parameter 31. Therefore, we'll move to line 20. We'll create a new node with the item 31 and its next pointer set to the current value of x next. So note that x next in this invocation is referring to the object that holds 41. And so we'll set the next field of the new object to refer to the object with value 41. On line 20 then, we're going to stitch this item in between, so we'll update x next, that's the pointer of the object with 21, to refer to the object with 31, so we stitch it in, and now it's in place. At this point, our functions can return. Note that on return they do nothing. This is computing going forward. All of the work of this recursion happens going forward. And we have a single call, in this case it's call number 4, which both creates a node and then puts it in the correct place. So Call number 4 here is really doing all the work. Everything else is just getting us there. This is a non-nullable recursion because the parameter x is never allowed to be null in this code. Note that if we ever called insert h with x equal to null, we would get a null pointer exception when we tried to access x.next. This recursive function behaves just like a loop. It does all of its work going forward, and in one iteration of the loop, we create a node and put it in its place. Recursion is more general than looping, so it opens up new opportunities that aren't available in loops. Rather than creating a node and putting it in its place in a single call, as I'm doing here, I can split this work between two invocations of the method. I can have my helper function return a node that it's created, and then the caller can put the object in its correct place. This is what this looks like. I have a node being created in my recursive function. Then that node is returned to the caller. There's two ways the helper function may be called. First, it may be called by the starter method, in which case I may be introducing a new first item, or it may be called by the helper method itself, in which case I may be updating x.next. Let's walk through this in the case that we are actually inserting something at the beginning of the list. So if I'm trying to insert 11 into this list, what's going to happen? Well, we start here at line 15 by immediately calling the helper function. Note that I haven't done a null check here, so it could be null. We don't know. But in this case, x is pointing to a node with item 21. That's larger than my parameter item. Therefore, the condition is true and will execute line 20. Line 20 calls the constructor, which will return a new node with item equal to the parameter and with a next pointer equal to x, whatever that happens to be. So x here is a pointer to the node 21. Therefore, the next for this new node will point to the node with item 21. Then, after finishing the creation, we don't immediately put this in its place. Note we're going to return back to the calling function. On line 15, we'll then take the return value we've been given, that's this new node, and we'll actually put it to be the new first. So note that when I update this first, I'm going to update it so that 11 now, or the node with 11, is the new first. And note that that's going to be fine. It's going to get my list in the right order. There we are. Backing up to the moment where the helper function returned, we can see the helper function here as returned the item, and we're about to put that in place. There are two separate function calls involved in this creation. The sender actually creates the new node. That was call number 3 in this case. And the receiver puts it in place. That's call number 2. Note that the receiver is not necessarily always from the same method. In this case, the receiver is actually the starter function. But as we'll see in our next example, the receiver might also be a call to the helper function itself. Let's look at what happens when we try to put 31 into the list with 11, 21, etc. In this case, again, we're immediately going to start our helper function. On line 19, we'll check whether x is null. That's false. We also check if the item referenced by x, that's in this case 11, is greater than or equal to the parameter. You'll see here that's false, and so we'll go to line 22. Line 22 is going to do a recursive call. When we do the recursive call, the value of x here in call number 4 is going to be the item 22. Note that the value of x in call 3 was the node with item 11. In call number 4, we'll again check for the nullity of x and do a comparison. And you'll see here that what we're comparing to is not x next item. We're looking at x itself. We're comparing 31 to x item, which is 21. And the comparison fails, so we'll go on and do yet another recursive call. In call number 5, x is pointing to the node with item 41. And in this case, the comparison on line 19 is going to succeed, and we will go ahead and execute line 20, because at this point, the item we're looking at is actually greater or equal to the item that we have as a parameter. And so we'll create that new node, and the new node is going to have the item parameter 31 and the current value of x. Note again that I'm not looking at x next. I'm looking at the current value of x. This new node is then returned back to the previous call. This is something I can't do in a loop, but it's very easy to do in a recursive function. Here, call number 5 is going to return back to call number 4. And what call number 4 is going to do is to stitch that item in place. Once we've got the item in place, now our functions can all return. Note, however, there is a wrinkle. Our functions called the helper without knowing whether or not a new object would be created. And therefore, it's necessary to copy references as we go back. It's important that this function actually returns something back to its caller. So on line 23, call number 4 will return its value of x back to the caller. This is a way of call number 4 saying to call number 3, hey, nothing changed, keep me in my place. In this case, we're sending the same node back to the receiver that the receiver had in the first place. So that receiver had as x next this node with item 21, and we're simply going to pass that same node back. So what happens here is line 22 doesn't actually do anything. Likewise, when we go back to the original starter function, we'll tell the starter function what's the value of first, because it might have changed. In this case, it didn't, so we'll simply pass back the old value of first, but the starter function doesn't know what it's getting, and it will simply put that in place. In this case, again, this line has no effect. This style of coding is very powerful and very general. And as you can see, it allows me to avoid a lot of duplication that I had in my non-nullable version of the code. It's worth studying the differences between these two styles. First, note that the function calls themselves haven't really changed that much. On line 15, I'm calling insert on first, and I'm doing the same thing here. The only difference is that I'm storing the resulting value as well. So in the non-nullable version, my helper function just returns nothing. In the nullable version, my helper function is returning a node, and I need to store that back. The same thing is true for the recursive call in the helper. The recursive call in the helper looks pretty much the same. The arguments haven't changed. The only difference is that I'm going to save back the result that I'm given. In addition, I need to return the current state back to my caller so that my caller can update their node on line 22 when they get there. The main change then is at line 19. You can see in the nullable version, I'm of course checking whether or not x is null, whereas in the non-nullable version, I'm checking whether x.next is null. Similarly, in the nullable version, I'm looking at x.item, whereas in the non-nullable version, I'm looking one ahead. You can see this entire non-nullable recursive code is always looking one step ahead. And this is because of the basic structure of a linked list. You have pointers going forward, but in this case, there's no pointers going back. So you need to wait back so that you can modify the previous pointer when you get to the node you need. There's no need to wait back in the nullable version. I simply am going to barrel forward, and then at the point that I need to create something, I'll return that back to the caller. In this pattern, I'm actually going backwards, not using a back reference in the list, but using a recursion. I'm able to send data back to the caller who's at the previous node in the list. Whenever there's more than one way to do something, it's important to know which one you're using. A very common error for beginning programmers is to loop on the nullity of x rather than the nullity of x.next. That's true both in the non-nullable recursion and in the looping version. Very common for students to look at x and x item rather than looking at x next and x next item. It's important to know when you're going through a link structure that you need to hang back one link in order to update what's in front of you. Once you understand the nullable recursion pattern, it's actually the easiest of these to write because it has the least amount of code. But there's common mistakes here as well. The most common mistakes have to do with updating links. For example, forgetting to update first as the result in the starter function, forgetting to update x.next with the result in the helper function, forgetting to return x. Using this pattern to mutate lists is quite powerful, and you'll see it again next quarter when you're looking at balanced trees. The main power here lies in the fact that we're doing computation both going forward, looking for the place to do something, potentially creating the thing when we need it, and then we're also doing computation going back. In this particular example, the computation going back is trivial. We may either put something in its place or we're simply copying the links that we had before. In the case of balanced search trees, which you'll see next quarter, the computation going backwards is much more complex because we want to maintain a balanced structure in a tree where we have potentially two children. Therefore, as we go back up the tree, we may need to change the structure going backwards. By mastering this pattern now, you'll be well prepared for dealing with balanced tree algorithms next quarter.